In this lecture, we will derive Kirchhoff's voltage law from the basic equations. Now, in electrostatics, we have studied that the curl of electric field is equal to zero, or by Stokes theorem, the closed loop integral, line integral of electrostatic field is equal to zero. Now, in my previous lecture, I have told that E is equal to J over sigma. Actually, J is equal to sigma is simply the point form of the Ohm's law. So E is equal to J over sigma. So if I put this value here, now if only this electrostatic field existed and this current density was because of just electrostatic field, then we can see that this J by sigma dot dl should be equal to zero. What does it mean? It means that the total current, the line integral of this current density along a closed loop, or if I say in other words, that only an electrostatic field cannot maintain a non-zero current. That is, it cannot maintain a current in a closed loop in the same direction, because it is equal to, the total thing is equal to zero. So if only there was only conservative electrostatic field, then there could not have been any closed loop currents. Now there must be some source which is non-conservative in nature, which should supply or which should enforce this circulating current or current in a closed loop. Now, how am I so sure that this should be a non-conservative field? That is because that in electrostatic we have seen that the potential energy does not depend on the path taken. Now we know that in a closed loop we arrive at the same point. So you see that the electron or the charge carrier in the conductor are neither going to gain energy or lose energy if it was just an electrostatic field. However, we know that in a conductor there is production of heat because of Joule's heating. So because of that Joule's heating, there will be loss of energy by the charge carriers, and that energy should be provided by some other kind of source, and that should be now non-conservative in nature, because it should depend on the path taken. Otherwise, there should not have been any neither loss of energy or gain of energy by the charge carriers. So it implies there is some source which is going to create some non-conservative field, electric field, because it is going to push or force the charge carriers. So some source of non-conservative electric field should be there in the circuit to force a circulating current in the loop. Now let us try to see that thing in the detail. So in a battery, what happens? Let us say these are two electrodes. This is electrode 2, this is electrode 1, and this is electrolyte. Now, because of chemical reaction, the charge carriers, let us say electrons or maybe some other kind of ions also, the charge carriers are pushed. Let us say the positive charge carriers are pushed on this electrode, and negative charge carriers are pushed on this electrode. So we see that the electric field created by that chemical reaction is pushing positive charge carriers in this direction, negative charge carriers in this direction. It implies the field created by this chemical reaction, or the impressed electric field, is in this direction. Now this accumulation of charge carriers is going to create a field from positive to negative direction. So this is the electrostatic part of that field. Now since when this battery is open, there is no flow of current. So it implies EI plus E should be equal to 0. It implies that the impressed electric field, which is non-conservative in nature, should be equal to minus of E, which is the conservative field. Now we define EMF as the work done per unit charge, because this impressed electric field is doing work, and that is being stored in the charge carriers or as potential energy. So this field is working when charge is moving from electrode 2 to 1. So this is called as the EMF. You should note that there is neither a negative sign in front of it, and we should see the limits of integration from electrode 2, that is negative electrode, to the positive electrode. So this is the EMF. Now we will use E is equal to minus of, this is EI. So this will be minus of E dot dl from 2 to 1. Now this is the definition of electrostatic potential, which is equal to V12. So you see that the EMF created by the non-conservative field in the battery is equal to the electrostatic potential between these 2 points because of the electrostatic field. Now, you know that if I close this circuit by connecting some external resistor or some conducting material which is ohmic in nature, then we know that this E is not equal to 0 in the battery as well as outside, that is in the conductor. But the impressed electric field is just present in the battery and it is not present outside. So we can see that if I write E dot dl is equal to 0, then we are seeing that we have to integrate this electrostatic field from electrode 2 to 1 inside the battery and then 1 to 2 outside the battery. That is E dot dl inside battery plus E dot dl outside battery from 2 to 1, from 1 to 2. And also, as I already proved, that this EMF is equal to V1 minus V2, or the potential due to the electrostatic field. Now, in the point form of Ohm's law, which we derived in our previous lecture, I told that this field is the resultant field. So you see that now this equation should be modified to take both the non-conservative field as well as the conservative field. So I should write it as J is equal to E, the electrostatic component, and the non-conservative component. Now, if I take this curl or the line integral along the full closed loop, I can see that this can be now broken as E dot dl closed loop plus EI dot dl closed loop. Now this is equal to 0, but this is just equal to the EMF induced. So you see that this EMF induced is equal to, now this J is because of both the electrostatic as well as the non-conservative component. Now, if I write J, I am assuming that current density as well as dl are in the same direction. So J dot dl is just simply JL. So if I write J as simply the current per unit surface area of the conductor, so that was this battery, that was this electrode, and this conductor is connecting these two electrodes. So the cross section is S of this conductor, and current density is also in this direction, and dl is also in this direction. So this integral of dl is going to give us the total length of this conductor. So JL is going to give us this. So J by sigma L is going to give us this one. So JL by sigma is equal to I by sigma S L, or I can write it as L over sigma S I, or it is equal to the resistance of the conductor into I. And we saw that the left hand side of this equation was equal to the EMF because of the impressed electric field. So this is the Kirchhoff's voltage law, which states that the voltage drop along a loop across the resistances is equal to the EMF in that circuit. That now let us say there are more than one battery connected in the circuit. So this V will now comprise of both. This is V1, this is V2. So this will be V is equal to V1 plus V2. So similarly, if there are more than 2, so I can write it as Vi over all the batteries should be equal to Ri drop. Or in words, I can write it as that this KVL, Kirchhoff's voltage law, states that in a closed path in an electric circuit and steady conduction, the algebraic sum of the EMFs, although it is called electromotive force, but it is not a force. It is having the same unit as that of potential, because I've shown V is equal to V12, the electrostatic potential. The algebraic sum of the EMFs is equal to the algebraic sum of the voltage drops across the resistance. So we see that this applies to any closed path in the circuit. And we can trace the path either in this direction or in this direction, because we took any arbitrary direction while deriving this result. So this is the basis of Kirchhoff's voltage law in circuit theory. Now we should clearly understand the difference of the electrostatic potential and the EMF. EMF is because of the non-conservative field, and it is equal to EI dot dl, that is the impressed electric field that is non-conservative in nature. And we can trace this loop in any direction. It should be equal to the drops along the loop in the resistances, and it should be valid in any loop of that circuit. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.